Well, welcome to lesson 22 of this Arduino C++ series, and today we're going to be using the 74HC595N shift register. That's a mouthful. I'll probably just call it the shift register through the video, and we're going to be using this to be able to add extra output pins to our Arduino or any other processor that you have. So going over to the workbench, the reason I'm working on this project, this is my model railway control panel that I'm working on, and I think now this is an early prototype. I think I now need about 70 pins. Now 70 pins isn't even available on the Mega. So that's why we're going to be using again some chips. These shift registers are what's called a shift out. In lesson 21, we used the shift in type shift register that allowed us to add extra buttons or switches. So today we're going to be driving some LEDs. Now, I only had room for 3 chips on the breadboard, so we've only got 24 LEDs running. However, you'll see in the circuit diagram that we can add as many extra chips as we need to. So the first thing we're going to do is go over to the resource page for today's lesson, and that's on the link just under the video, or as you can see on the bottom of this splash screen. So let's take a look at that now. So today's lesson, there is the code to download, and obviously we have the 2 diagrams. If you click on the diagram, you get the larger version. Now, I have done a diagram for the chip itself. If you're wondering what this little mark is here, I actually put some red nail varnish onto my chip so that I know which corner the V+ pin is. It's just a little thing that I've done over the years and make sure that I don't ever put the chip in the wrong way round. You are supposed to use this little semicircle here to align the chip, but obviously sometimes when I'm working can't quite see it, so I put the little mark on just so I know. Right, let's take a look at the circuit diagram itself. Now, because we're powering a lot of LEDs, and I've only put LEDs on the first 2 chips, I haven't put any on the last chip because the diagram just goes on and on, but basically you can repeat this setup for chip 1, repeated on chip 2, chip 3, chip 4, chip 5, however many chips that you require. Now, the first thing I'm going to start with is the power supply before I forget. Now, these chips can be 3.3 volt or 5 volt tolerant, feed it whatever you want. However, just a little bit of a warning. I've got 24 LEDs working, and I am using the power supply from the Arduino. However, if I was doing a really large control panel and I'm up at sort of 40, 50, 60 LEDs, and there would be other things that the Arduino would be expected to power, at that point I wouldn't take the 5 volts from the Arduino. I would instead use an external power supply. Now, the external power supply, if you're using an external 5 volt or 3.3 volt supply, make sure that you then disconnect the Arduino's power supply. The circuit only has one or the other. It does not want both. That's going to be a bad day. So just one power supply. Now, I'm doing this with the Arduino Uno. That's a 5 volt board. If you were doing this with an ESP32 or an Arduino Duo, those are 3.3 volt boards, and therefore that power supply needs to be 3.3 volts, because you do not want anything connected with 5 volts going directly to a 3.3 volt pin, because that will be a bad day. Right, that's the power supplies over. Let's get on with the rest of the circuit. So apart from the power supply, the only connections, there are 3 pins. Now I am using pins 10, 11 and 12. You can change them to whatever pins you want. The reason I'm using pins 10, 11 and 12 is I still have the circuit set up for the switches using the shift in register, and that was written for pins 7, 8 and 9. So in a future project I'm going to combine the two setups together so that we can control the LEDs, the outputs, with the inputs, and that's the reason why I've got them in pins 10, 11 and 12. Now the way this works, the three connections, there is the first one, which is the latch pin, which is the white, that is connected to this particular pin here. If we look on the circuit diagram, you can, on the chip itself, you can see the pin there. The latch pin is the pin that says, right, okay, we're going to now prepare the chips to receive data. So when the latch pin goes low, we then pump the data in. Now, as a byte of data goes in, which is sent in using the data pin and the yellow clock pins, as that data is pumped in, the previous byte of data that was in here gets pumped along the line to the next chip if there is one. So if we're using a single chip, we just pump one byte in. If we want to use 3 chips, we're going to put the first byte in, then the second byte, and the first byte will go to the next chip. Then we're going to pump it again. This data is going to go to this chip, this data is going to this chip, and the new data will go in the first chip. Now, thankfully, all that's going to be covered in the code in an easy to use method, but that is basically how it works. So the latch pin opens the system and starts allowing the data to be pumped into the chips 1 byte at a time. And then when the latch pin, if you like, we close the door at the end, the chips all then will display the new settings. They do not display the new settings until the latch pin gets reset. Now, one other thing, obviously there are 8 LEDs. They are pins 0 to 7 on the chip. It's, once again, it's one of those odd setups. It would be really nice if they put 0 to 7 on one side of the chip, but they don't. So 0 is up here, and then 1, 2, 3, 4, 5, 6 and 7. And if we go to the pin out of the chip, I have tried to give a slightly better view of how that works. Apologies for the bent pin in the photograph. Now, one of the good things about these chips is they are dirt cheap. We just whiz over to eBay. First one on the list, I haven't even really looked these up, but £3.39 for 5. So that's going to give you an extra 40 pins, or you can splash out and spend, what, £6, £7 and get another, what's that? That's going to be 80 pins. Or get them from China, and you're going to get them even cheaper. So as you can see, these are really, really cheap items and a very easy way to add extra pins to any processor board. Now, going back to the webcam, one of the issues with these, and I should remind you, the resistors I'm using here are all 330 ohm because that's what the LEDs require. But as you can see, the breadboard becomes quite a sort of a bird's nest of wiring. Now, it's fine on the breadboard to have it like this because it doesn't matter if the connections come loose. But when you go to build a proper project, if you're not going to have your own PCB made, which if you're doing a one-off, why would you? But what I tend to do is use this sort of Vero board type material. This one has the tracks in long strips. There's others where it's just individual tracks. For these particular chips, I'm going to use the one with the strips because I actually think it will be easier to solder the project together. So that's how the project is working. Let's see how I got there, and let's move over to the Arduino IDE. So the first sketch I'm going to do is basically a connection test. Now, this sketch is going to be written just using a single chip. If you've got the other chips, you can leave them connected, but you will see some odd, funny effects because the other chips will display the last value of the chip that you're working with. But I'm just going to show you the output of this so you can understand what I'm trying to do with the code. So the idea of this bit of code, it's just going to increment a number between 0 and 255. And as you can see, basically what we have is a binary counter. It's just working up and it's testing all the individual pins to make sure that they all work correctly. Now, I'm not going to bore you with waiting till we get to the end. Let's get on with the code. However, one thing I forgot to mention, I have disconnected this blue wire so that it's no longer feeding data to the second chip so that you don't get the weird effects with the other LEDs. So in this sketch, we're just going to make sure that our bird's nest of wiring is working correctly. Right, we have our 3 pins. Now we have a latch pin, a clock pin, and a data pin. And normally I would just call them latch pin, clock pin, and data pin. However, this time I have added the prefix out. Now the reason is that I'm going to connect the last sketch with the shift in shift registers, and they already are using these variables. So rather than messing around and getting people to alter sets of code, I just thought I'd start with the names changed to make life easier. I've then got a single byte. Now a byte can hold a value between 0 and 255. When it gets to 255, if you increase its value by 1, it doesn't become 256, it becomes 0 again. So that's why these LEDs will flash until all of them are lit, and then they'll go straight back to none of them being lit. We're going to be using millis for timing. Now, all the sketches I do will use millis. That's because we want non-blocking code. There is no use of delay in this code, because if I use delay, especially when I start to add the buttons, it's going to be an absolute nightmare because the buttons won't work. Now, if you don't know how timing works with millis, it's back in lesson 3. Right, in the setup, start the serial monitor because we're going to output some information. And this time, all the pins, the pin modes are set to outputs. So coming down to the main loop where the business starts, we've got the timer using millis, nothing particularly important there. Now the timer I'm using, we're going to be using 1000 milliseconds, so 1 second. So every second it's going to change the LED setup. And all it does is it increases the value of counter. So counter increases in value, and because it is that byte, as I said before, when it gets to a value of 255, the next value it will get is 0 because it will have run out of space. It will go back to 0 again. Then what I'm doing is I'm going to serial print out the decimal version of the counter and the binary version. And at the same time, we're going to send this byte of data to our chip. Now, we are setting the latch pin low. So if you like, we are now saying to the chip, we're going to send you some data. Then we're going to use the shift out function. And the shift out function has 4 variables that are sent to it. Obviously, it needs to know the data pin, the clock pin, and then you get the MSB first, and then the counter. Well, the counter is obvious, that is our value, but the MSB first is the most significant bit. we could put in the LSB first, the least significant bit. What is it talking about? Right, let's have a look at a very simple word processor document. Here we go with some bits and bytes. So a byte is made up of 8 bits. Basically zeros and ones. If we have, as we see here, 8 zeros, then obviously the value is 0. If we have 8 ones, that is the equivalent to a value of 255. Now, we are not worried about the numeric value for this setup. The way this works for our chip is if the pin is 0, then it switches the LED off, the pin goes low. If we send a 1, that pin goes high. So with our sketch, the most significant bit, if we have MSB first, then this value is sent first. If we have LSB, then it will be this value that is sent first. Now, it wouldn't make any difference on those two, but of course with these ones it would give a completely opposite order to the way that the pins are set, high or low. So whether you want MSB or LSB first really is up to you. I find that MSB first helps me in a more logical way because I'm thinking, right, the whole number is moving through in the correct order in the way that I think. But that's a personal choice and use that according to your project. Now going back to our code window, once I have sent the information, the byte of data, those 8 bits, then I'm going to set the latch pin high, and that is going to say then to the chip, you now have the correct information, now process that information and set the pins according to the byte of data that you have. The pins do not change their setting until this line happens. So I've uploaded the code again, and as you can see in the serial monitor, down here we have the decimal value and then next to it the binary value. And the LEDs that you see, if you can sort of watch both at the same time, you'll see that the LEDs are following the same pattern as we are seeing in the binary value. What I'm going to do now is just change the code, and we're going to set this line instead of the MSB. So let's just set that, upload the code. Now watch what happens with the LEDs. So now you notice as they start, because we're sending the lowest bit first, you can see that the LEDs start progressing from the other end of the pin. So in other words, the chip is receiving the data in the reverse order. Now I'm going to be using MSB because it makes logical sense to me, but I just wanted you to see that so you understand the difference between the two. However, the good news is I've now tested all the LEDs and I know that my bird's nest of wiring is working correctly. So for sketch 2, you can now see that I've got all of the LEDs flashing from all the chips. I've reconnected that blue connection. So now I'm sending data to all 3 chips, and I'm sending a different set of data to each chip, just to give you an example of how you can manipulate all of the LEDs at the same time. So looking at sketch 2, once again, they were using the same 3 pins from the Arduino. We never need to use any more. But instead of having 1 counter, I've now got 3 different counters. Now, this is going to just show you how, if you like, to send data to the 3 chips. The problem is, if I'd got 6 or 7 chips, this is going to get messy. So we're going to look at how to send the data to the 3 chips, and then I'm going to show you how to create some functions that make all of this very simple to use. Now I'm still using the same timer, and once again the setup is identical. The main difference is when we come down to the main loop. So as we come into the main loop, once again the timer is going to remain at 1 second. Counter 1 is going to replace the old counter. That's just going to increment by 1 each time. Counter 2 is going to increment by 5 and counter 3 by 7. The reason I picked an odd number was to make sure that the very end LED always gets lit and unlit, because if you pick an even number, one of the LEDs on the end will never light up. I'm then going to serial print out the values, and you can see it here. We've got the first chip counter going up by 1 with its binary, the second one going up by 5 with the binary value, and the last one by 7 with the binary value. Again, the reason for picking those odd numbers was just to make sure that all the LEDs get lit and unlit at a certain point. So now we're going to come down to the sending routine, and I'm going to show you an error first. It's a very easy mistake to make. So the latch pin, as before, is set low, and then we start sending the data out, and then when we finish sending the data, we send the latch pin high. Now the way I'm going to send this, I'm going to send counter 1, then counter 2, then counter 3. Let's take a look at this and how it outputs. So here is the output, and I hope you can start to see the problem. Counter 1, which I want for the first chip, and for me the first chip is this one on the far right, is supposed to be incrementing by 1, but it's not. This chip over here is incrementing by 1. This is the chip that's incrementing by 7, and obviously the center one is incrementing by 5. Now the reason for this is the way that the code is written, and it's something that beginners often do. It would make sense that you send the first chip's information first, then the second chip, then the third chip. That is wrong, because what happens is it sends the data to the first chip, then we send the next set of byte of data, so it moves that byte to the next chip and it fills this one. Then we send the third byte, which moves the data from here to here and the data from here to here. So the information that we send first needs to be the information for the last chip in the line. So I've re-uploaded the code, and the first thing that is the big giveaway is if we look at the incrementing by 1, we can see that is running nicely in the right hand side. So now I am sending the final chip's data first, then the second chip, then the first chip in the line. Just something to remember if you're writing your own code. Now, nice as it is to be watching LEDs flashing on and off, what we really need when we're building a project is we want to be able to send an instruction, and my goal is to be able to, if you like, turn on and off individual LEDs either as a group or individually, and I want to be able to address the LED individually. I want to call that LED LED 8, I want that to be LED 9, 10, 11, and moving up. What I don't want to have to do on my project is go, okay, that is LED 3 on chip 0 and that is LED 3 on chip 1. That's not the way that I think logically. So what I've done is written you some functions in the next sketch to make all of this much, much easier. So if you like, in the first two sketches, we've learnt the theory of shift registers. In this sketch, I'm now going to show you how to use a couple of very, very simple to use functions that can be expanded to as many chips as you require. Now, the first thing that we're going to use is a definition. Now, a definition is different to a variable. Now, even though these variables here are a const int, that means it is a write protected variable. That is different from a definition. A definition, when the code compiles, basically does a word processor type search and replace, and wherever it sees this line, it replaces it with a 3, and that happens at compile time. Now this means that when I create an array, now if I put my cursor over, you can see that value num 74HC595 chips 3. That means that this information here will be replaced with that 3. So this array will be an array size of 3. Now the reason I've done it this way is it just allows you to change this to however many chips you want. I think from my control panel is going to be 4 or 5. I'm not sure yet. It wouldn't matter if it was 20. It would be just literally change that line. That will then deal with all of the array setup. I'm then setting up a variable which is send byte, and this is going to tell the system when to send the byte. I'll just put a move that down a bit there. So that is, if you like, the bit of code for setting up the chips. The rest of this code here is purely to make a demo run without me having to have lots of buttons. So once again, for this demo, we're going to use a counter set at a 1 second interval. Once again, setup is absolutely identical. It's when we come down to the main loop that things start to change, because what I've done is I have created some functions that I have put down at the bottom. There is one function that is going to process the chips. There is another function here that is going to write to the chip. Now, what I have tried to do is imitate the digital write. So if you think on a normal pin, if you wanted to send some data to it, we would write digital write pin 8 high. Okay, and that would send pin 8 on our Arduino to a value of high. If we had an LED attached, the LED would light up. When I'm calling this function that I've created, I'm doing exactly the same, except that W, the value that it gets sent, is the pin. Now the pin, in my case, if we go back to the webcam, the pin is not the pin number on the chip, but it's literally 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and so on. So I just want to send the number of the pin in the list of pins rather than having to work out which chip the pin is actually on. So going back to our code, how is this going to work? Right. In the main loop, I've got two variables that I've set up. I've got my counter, so it's once a second. And what I'm going to do is I am going to send my counter high. So what this is going to do is it's going to send the pin with the value my counter high. So it's going to work through all the pins, then it's going to increment that counter. So it's going to start at 0 and keep increasing in value. And it will keep increasing in value until it gets to the number of chips times 8, which means it's run out of pins and it needs to go back to the beginning. And when it goes back to the beginning, then it's going to set all the pins low. So this is going to work as a counter again, but it's going to show you how I can set each individual pin. Now, the way this works with this first function, it receives the pin and the state. So just like you would do a normal digital read, within the function at the moment, it's going to serial print out that information so you can see the data that's arrived. Now, if the pin state is greater than 0, we're dealing with any weird values here. This is accidentally if someone goes and types in 10, it should only be high or low, but if someone goes and types in a 10, if it's greater than 0, it's going to change that value to 1, and if it's not greater than 0, it's going to put a value in of 0. So this little section here is just a sort of a little bit of checking for errors, and in the same way, the pin value has got to be a legitimate pin value, so it's got to be greater than -1. So in other words, I want a value between 0 and it's got to be smaller than the number of chips times 8, because our number of pins, although it's 24, our pins are numbered 0 to 23. That's how arrays work. And once again, if you don't understand arrays, they were covered back in lesson 9. So it's then going to go through the chips, and this is, if you like, where the little bit of magic happens. It's just in this little while loop here, because if we send a value of 10, then 10 is looking for pin 3, so that's 0, 1, 2, which I'm going to call 3, on the second chip. So this actually works out, this little while loop figures out which pin it's going to be on which chip that it's going to send the instruction. And what it then does is it updates the information in this array, which is storing the bytes of data. So that is updated here. So what we use is a function called bit write, and bit write, it says, right, this is the variable, so this is the byte of data that I'm going to update. I'm going to update the a certain bit of that data. In our case, we're going to give that the value pin, and that is going to have a state. So going over to the Arduino reference, it's this that we are doing here, bit write, and as you can see, it has 3 parameters. Now, if I can bring up my word processor document again, the way that this works, let's just try and shrink that down and get both up at the same time. There we go. So the example is the numeric variable to which to write. So this is, if you like, our byte of data. We've got 3 bytes of data here. So we're going to say, right, we're going to change this current byte. So we pass over the variable name. Then we're going to say which of the bits we're going to write 2, starting with the least significant, the rightmost bit. So we start here with 0, 1, 2, 3, 4, 5, 6, 7. Then we're going to set it either 0 or 1. So if we were to send over 3 and 1, we go 0, 1, 2, 3, and 1. That would send that to a value of 1. If I set it to 0, that one would have been changed to a 0. So we can literally manipulate the individual bits in the byte. Now, thankfully, you don't have to understand all of that to use these functions, but if you do want some more tutorials on manipulating bits in bytes and various variables, then let me know in the comments and I'll do a separate tutorial on that. But once we have, if you like, set the value in the byte, then there's this variable send state is set to 1, and this lets the system know that a byte of data has got a change of value. Now, one thing I have done here is I've put an else statement in. This is the if. Is the pin a valid pin? If it's not a valid pin, it's actually going to serial print out you've made an error. In other words, you've told it to send some information to pin number 25 and you haven't got a pin 25. Send the wrong stuff. Right. So that is the function that is used to set the data. And again, from a user point of view, you are just using it just as you would use digital write. You can use it to set your information. And then in the main loop, the one thing that you've got to have is this call to this function, process 74HC595 chips. That must be in the main loop. And that is this function down here. And all this function does is it checks to see if any change has been made to the value of send state. So as you use this function, it changes the value of send state to a 1. And if this function says, whoa, hang on a minute, send state has increased in value, it's now a 1, that means we've got to send some data to reset the LEDs. It will reset send state ready for the next function call when the next pin is changed. But in the meantime, it's going to send out all 3 bytes of data because I've got 3 chips. Notice it's for Q equals num74HC595 chips. That is my definition that I put in. So obviously if I change that definition to a 5, this would go through 5 chips. If I'm only using a single chip, and this works with a single chip, it will be fine. It will just do the 1 chip. Now I've set it to MSB first. If you want it to do LSB first, then comment out that line, uncomment that line. And then all I've got is this serial print and I'm resetting the latch. So that is how the system works. And let's just watch the demo in action. So all this is doing is as the counter increments, it is lighting the next LED. It's working through the whole line of LEDs. And when it finally gets to the last LED, it will turn them all off and it will start again. Now you'll notice the very last LED doesn't really light up, and that's because as soon as it lights up, it's told to unlight because all the LEDs are lit. But it does work for a microsecond. Now once again, this is just creating a pattern. What I want to do for the final sketch is show you how to use the function in what I would call a more project type system, the way I would use it in a control panel, or in the case of the final project, we're even going to look at doing a railway crossing at the same time. So sketch 4, once again, using 3 chips. this is, if you like, the information for setting up the chips and the variables that are required. Down at the bottom of the sketch, I have left in those two functions, although you'll notice within the functions now I've commented out the serial print statements because it makes them run faster. It's not great to leave all these serial prints in all the time. In fact, those should be commented out as well. They can be quite useful just to see what's going on while it is running. Now, the way this is going to work, going back up to the top of the sketch, I have got current millis, as always, for timing. I've then got a counter timer. This time it's going to be changing every 200 milliseconds, but I'm also going to simulate a railway crossing. Now, a railway crossing, the one up the road from me, has 4 LEDs or 4 lamps. Some of them have 8, but we're going to do this for 2 for starters, and we're going to make them flash alternately, so 2 are going to be on and 2 are going to be off. As before, the setup remains the same. It doesn't matter how many LEDs we're going to be manipulating, the chips still connect through the same 3 pins. Now moving down, let's have a look at the first setup. So the first one is the crossing millis. Now the crossing, if you remember, that's going to move every 1 second. And this gives you a better idea of how I would use this system. So what I want to do is I'm going to, every 1 second, if the crossing state is high, it's going to set it to a 0. If it was a 0, it's going to set it to 1. This is just so that it keeps swapping its, if you like, its state. And I'm going to set pins 0 and 7 are going to be high, 16 and 23 are going to be low. And on the opposite second, in the next second, it'll go 0, 7 go low, 16, 23 go high. So you'll see 2 LEDs on the first chip flash alternately with 2 LEDs on the last chip. And again, if I wanted to add more LEDs in, I can just add it in as I desire. Now, the reason that I've set the timers at different rates was to show that you can have multiple things being driven by the same board very, very easily. So now what we're going to do is look at the green LED counter. That's going to be running in the center, and that's going to go back to that old method where it is just going to go work its way up through the LEDs. In this case, we have to start with a value of 8 because the LEDs in the loop are going to go, they're going to keep incrementing while the counter, if the counter gets to 15, goes over 15, then it will go back to 8 again, because if we go to the webcam, the counter is just going to be running across these center pins, as you can see. Now, one of the things you'll notice with the counter this time is that all of the LEDs don't light up together. It's just one moving across. So as an LED is lit, the previous LED is turned off, and I'm just going to show you how to do that in the code. So looking at our code, with the counter, this is how I set the counter. So as the counter comes across, we're increasing this value, but we're sending this equivalent of a digital write to the pin with the value of counter. Now what I then do is I then send a value to another variable called last counter, and I set that low. And after I've sent those instructions, last counter equals counter. So whatever pin I set high, that value, the value of last counter, will be set to that value. So the next movement, that pin will be set low while the new pin is set high. That way you'll constantly see only one LED appears to be lit. And obviously it then just keeps working through all the pins, and when we get to a value of greater than 15, it then goes back to the beginning and sets counter to 8, and that means it'll just keep cycling through those center green LEDs. Finally, of course, in the bottom of the main loop, we've got that call to process the chips, and this calls this function at the bottom that we don't actually have to do anything about, but that deals with sending data as it needs to be sent. So going back to our webcam, we then finish up with the center chasing its tail while these two outside setups just flash the LEDs in an alternate, if you like, crossing barrier type style. Now, once again, all of this has been controlled by time, which again, if you wanted a crossing barrier, that's absolutely fine. This sort of bit of code will do. If you want more LEDs on your crossing barrier, you just need to increase the number of LEDs that you call in here. Obviously, I did two completely different chips just for the example. Probably if I was doing a crossing, I would be using one chip in maybe a series of chips. But the other thing that I want you to think about at the moment is these are being controlled by time. If in my control panel, this would be where if a digital input is received, if a button's been pressed or a sensor has triggered something, then I might set something. So if I was on a control panel, changing the direction of my track, I might set one LED high while I set another LED low, or if something on the layout is turned on or turned off, again, a particular LED can be set high or low, and it's literally using this function. So that's it for today's lesson. We've reduced the control of multiple chips just down to sending a pin number and the state that we want it to be in. What I'm going to do in the next model railway tutorial series is connect the, if you like, the shift register that I did in lesson 21 with the buttons to this particular set of shift registers, so that you can see how to connect the inputs to the outputs. So if you want to see that, please click the like, subscribe, or make sure you've clicked the notification bell, or however it works, so you get to see that video. So that's it for today. Hope that has been useful to you. And as you can see, it is possible now to have almost limitless inputs and outputs from even your most basic Arduino. And as I said, in the next lesson, we will connect the two together. So I hope that's been useful. And if it has, please, click that like and subscribe, because it does help the channel. And I'll see you in the next video. Bye for now.